you ever wanted to visit the quantum realm? The good news is, you're already there.
There's no such thing as, like the quantum realm and the classical realm. Everything is quantum, bottom to top. It's just that the quantum part is sometimes hard to notice.
There are laws of physics everyone intuitively knows. Laws that Newton first described with precise mathematical language. Among these rules, everything has a well-defined position. No thing spontaneously jumps from one place to another. There is no fundamental limit to how fast something can move, or how gently it can be nudged. These seem so obvious it sounds silly to list them out, but the remarkable thing is that they are only approximations of true reality. We call these rules of thumb classical physics, but beneath them lies a deeper fundamental theory of nature that we call quantum mechanics, and it's far stranger than you could ever imagine. Take spin, for example. Most people think that when you spin something, there is no limit to how slow it can revolve. But most people are wrong. Spin comes in irreducible chunks. The slowest a basketball can rotate is one turn every 250 sextillion years. The next fastest speed is 2 turns every 250 sextillion years. These spin chunks are too small to notice in a basketball, but the effect is more obvious with lighter weight objects. A virus can only spin at a rate of once per second, 2 turns per second, 3, etc. But no in-between spins can exist. Looking at yet smaller sizes, it's more obvious that an electron's qualities like spin, charge, or magnetic flux are irreducibly chunked, or quantized. Electrons don't actually spin at all, yet still have an intrinsic angular momentum called spin up or spin down, and the weirdness doesn't stop there.
You can learn quantum mechanics, which is kind of the base code of the universe. And you can learn how that's done in a book, and you can even do some basic experiments. But you don't really appreciate it until you try to make something new out of it.
Today, scientists aren't limited to watching nature do amazing and weird things. They can engineer systems using these properties. They can make something be delocalized, neither exactly in one place nor the other, nor exactly in 2 places at once, what physicists call a superposition. They can entangle 2 things such that neither is independently real and only their whole combination has an independent reality. They can even tunnel or quantum leap something through a barrier and have it appear on the other side as if by magic. Superposition, entanglement, quantum leaps. A computer designed using the strange quantum nature of reality could have unprecedented power, and everyone wants one.
Quantum computers are rapidly coming into their own. We can see a path towards them replacing very specific computing hardware for problems like simulating large quantum systems. Right now, they're science experiments with a big dream.
The word computer is a little misleading. It makes us think that the computers are just like the classical systems that we have, but they're nowhere near that developed yet. So we are still trying to build the very basic building blocks.
In classical computers, information is at its most basic level, a bit, either a 0 or 1 state.
That's like your light switch being on or off, or more likely in a computer, it's a magnetic domain that's oriented up or down. When you're talking about a quantum bit, you now not only have something that's analogous to 0 and 1, up and down, but you also have the ability to be in superpositions of up and down.
Quantum bits, or qubits, can not only be in 2 states at the same time, they can share or entangle their states across many qubits, increasing their computing power.
You want a quantum superposition that is shared across many qubits, probably hundreds or thousands, until we have a quantum computer that beats what we can do with classical computers.
In classical computers, operations are performed on bits using tiny electrical switches called transistors, more and more of which have been squeezed onto a chip. As transistors shrink, quantum effects become more noticeable and can even cause classical designs to fail. But if you're ready for those effects, you can use them to your advantage and even make a single atom the basis of a quantum bit. This, however, is more easily said than done.
It's hard to get an atom to talk with another atom. People are doing it. That is one form of quantum computing. But a lot of the quantum computing that goes on in this lab is trying to use electronic circuits to emulate the same behavior as atoms.
The electronic properties of atoms can't be customized. Circuits, on the other hand, can be made any way scientists like.
We've become able to make pieces of metal that also have these discrete sets of energy states, at least when we make them cold enough.
The key ingredient to accessing a circuit's quantum properties is temperature. If you freeze some metals colder than the vacuum of space, they become superconducting.
The name literally refers to how you can conduct electricity through a metal with no loss. And the first time I heard about it, I thought that was the most important property of superconductors. But I would call it a macroscopic quantum state. The idea is that when you get cold enough, all these electrons start moving in lockstep, all doing exactly the same thing, right down to the quantum mechanical level. So even though it's a huge macroscopic number of electrons, it's behaving like one electron going around an atom, something you can almost get your hands on and touch.
And so an artificial atom, when we're talking about quantum computing, is usually a solid state system. In this lab, usually we meet a transmon qubit, which is a capacitor with an inductor.
These type of circuits are known as LC oscillators because the energy oscillates back and forth between two components like a bell.
Where the capacitor stores energy in the electric field and the inductor stores energy in the magnetic field, and the energy just sloshes back and forth. It's like the energy goes to the inductor, sloshes to the capacitor, back and forth.
But this is no ordinary LC oscillator. Its cold, superconducting metal suppresses the background noise to such a degree that the circuit's quantum nature becomes accessible. And at negative 459 degrees Fahrenheit, the discrete energy levels become clear, like the electron energies in an atom, but with properties we can design, name, and manipulate.
If you take all the energy out you can, so there's no sloshing, we just call that zero because we're unimaginative. And if you add the smallest amount of energy you can to that, we call that one.
Operations are performed on these qubits, not by arranging transistors like in a classical computer, but by nudging the qubits with microwave pulses.
It's kind of like trying to make a wine glass ring. It's not going to ring at any frequency that you can make. Similarly, our qubits are oscillators that have a defined resonant frequency, and it's only when we're hitting that frequency that they respond.
Say we wanted to push a system from the 0 state to the 1 state, we would put in a little tone of just that frequency to get that up to the first one. So far, so good. Now we're in the 1 state. If we want to go from the 1 to the 2, then we put in just the frequency that would go from 1 to 2. But that's the same as the frequency that goes from 1 back to 0. You could go either way. It might even be a superposition, and then you would just kind of lose track of where you are.
With evenly spaced or linear energy levels, a qubit would be impossible to control. So scientists use an unconventional, non-linear inductor with energy level spacings that are not alike.
So what we need is each of those energy splittings to have unique frequency. That's what the nonlinearity does for us. So the 0 to 1, there's a 0 to 1 frequency, there's a 1 to 2 frequency, a 2 to 3 frequency, and so on. You need to be able to individually address those energy levels. The way you individually address them is by having unique frequencies for every transition. And the way you have different frequencies every transition is to have a little nonlinear element.
This nonlinear part of a qubit is incredibly small. In fact, it's invisible to the naked eye.
So those two parallel dark lines make a planar capacitor. A capacitor is a device that will allow you to store electric energy. And then there's a gap in them where it looks like they're not connected, but in reality they are. They're connected by a very, very thin trace of metal.
This bridge is an inductor, but it's a very unique one. To understand why, you need higher magnification. You need the power of a scanning electron microscope. Zooming into the qubit reveals a strange stack of overlapping metal. This is called a Josephson junction.
The Josephson junctions are the magic that make our qubits work.
It is a layer of superconducting metals, just like a little layer cake, a layer of oxide that does not conduct electricity at all, and then another, if I had a third hand, a superconducting layer on top of that.
The way we make Josephson junctions is a bit complicated. We have to take an aluminum layer, a very well-ordered aluminum layer, then we oxidize it. Oxidizing is kind of a messy process. It's essentially allowing it to rust. So we take an aluminum layer, we allow it to rust, and then we put another aluminum layer on top.
And that seems pretty uninteresting because you can't have any current go through an insulating gap by definition. But if you make it thin enough, you get another one of these quantum mechanical effects where there's no such thing as the electron concentration just stopping hard. If they overlap enough, then you can get what's called tunneling, where they will just quantum mechanically, quantum leap, whatever you will, that's a term, jump from one side to the other.
This quantum tunneling is what gives the qubit its nonlinear energy levels.
That, in essence, means that when you change their amplitude, their frequency changes. The equation for them is actually identical to the equation of a pendulum. I have a pendulum right here, and we can perform an experiment. If I go and I start oscillating this pendulum very slightly, you'll notice that it's going back and forth pretty quickly. If I go and increase the rate of oscillation, the amplitude of oscillation, it takes longer to do a full loop. So the fact that I can change the amplitude and that changes the frequency is what makes our quantum computer controllable.
Meaning that if I want to switch one quantum bit from 0 to 1, I have a microwave pulse that corresponds to that. If I want to put 2 quantum bits into a superposition, I have another set of wave pulses that do that action. It is that set of pulses that do something that I know that we call a logical gate.
So why are quantum computers still experimental?
Well, on paper, quantum computing is solved.
The theory, which is a mathematical description, and the hardware, which is a piece of metal in this case, don't line up to every single level. And so anything where the theory doesn't match the physical system is something we call noise.
We have noise from everything around us. If you look at room temperature, we have infrared cameras that allow you to see in the dark. That, for us, is noise. Infrared will cause a whole bunch of noise on our qubits. That's why we cool them down to very low temperatures to try and isolate them from the room temperature noise.
Noise not only introduces errors into quantum computers, it can unintentionally change a qubit's delicate quantum state, a process called decoherence. So to separate them from their environment, scientists run their experiments in giant refrigerators that are more complicated than you'd imagine.
So if we're going to send a signal into our fridge here, it all starts on the room temperature racks on my right. They come up overhead and come in through the top of the fridge, through this very top plate, which is always at room temperature. On the outside is the regular lab space. On the inside, when all the shields are on, will be under vacuum. Vacuum is important because if there's any air in the fridge, that would transmit heat from room temperature to the colder stages inside. We pump out all the air, and then each stage gets a little bit colder all the way down to the bottom. So there's 37 lines coming in the input here. Our signal will follow one of them, little coaxial lines, and they all have a wiggle to them. That's for 2 reasons. One is the fridge will expand and contract a little bit as it changes temperature, and we don't want to put any strain on these. So that just can take a little flex and it doesn't damage the cables if they change in length slightly. The other is we're paranoid about any stray light getting in, some infrared light or something like that. Light won't bend around corners and send any photons we don't want into the fridge. This stage is at about 30 Kelvin. That is not a temperature that comes up in everyday life. The nitrogen in the air that you're breathing will turn to liquid at 77 Kelvin. Oxygen a little above that. Air is ice. The next stage is 3 Kelvin. At this stage, even helium, the last gas of anything, becomes liquid. Helium never becomes solid, fun fact. At this point, gases don't exist at this temperature, at 3 Kelvin. Now you're a solid or a liquid, there's no other choices. We go to even skinnier cables as we get down. Skinnier, just less metal will conduct less heat. We want to make sure that we don't conduct any heat from stage to stage. These are a metal that's a very low thermal conductivity, a copper nickel alloy, I think. And then we get colder to about 1 Kelvin. This is the still. This stage we actually add heat to. For all the hard work we do to try to get cold, this is the stage that we actually heat to get it to just the right temperature. Next stage, 100 millikelvin stage. Each one gets a curlicue down to the mixing chamber, which is at about 10 millikelvin, which is 30,000 times colder than room temperature on an absolute scale. And everything at this plate and down is at 10 millikelvin. So we have a lot of room to mount our little devices. And we have, I don't know, maybe 20 independent experiments on this at a time. You can see all manner of different filters and things here. Just to throw out any frequencies you don't want, let's just follow this one, for example. It comes in, you see it goes through this little collar, and inside this collar would be inside a shield. That is a magnetic shield. It's different than a Faraday cage. That's something where you can just block electric fields. It's actually not possible to block magnetic fields. You can only redirect them. And so it's actually a kind of metal that kind of sucks all the magnetic field lines into it so that there's a lower magnetic field inside and outside the can. In the walls of the can, the magnetic field will actually be enhanced. You just kind of redirect all those lines into the walls of the can, and then the space inside will be a very low magnetic field. So we might take something just to mount it just so, put some screws on there onto the paddle, and then I can open up inside. I'll just take the lid off. And this is a typical device. It has 6 coaxial connectors. You have a little chip with some quantum devices in the center. These 6 ports might, for example, be, in this case, the top and the bottom ones are the input and output for the RF. So our output lines, once we have some signal from our qubits, we'll typically go through a quantum limited amplifier and then go through these isolators. These are double junction, single junction isolators, basically one-way valves, cryogenic one-way valves, so that your signal to the hotter stages can get out, but any thermal noise from the upper stages can't get down to the lower stage. And then if we follow that signal chain out up to the 3 Kelvin stage, and this is where we have the first conventional amplifiers. We're usually trying to measure kind of single photon events. At room temperature, even in the microwave range, there's a lot of thermal radiation around. So we got to boost that signal up to a level to where something conventional room temperature electronics back at the racks like this can detect it and distinguish it from just thermal background. Amplification is the name of the game. Not just amplification, but very low noise amplification. Every kind of amplifier adds its own noise. That's both just an engineering truth, and we're at the level where we get the physics truth. You can actually quantify how little noise nature allows an amplifier to add, and we get as close to that limit as we can. And then it goes all the way to room temperature, and we have more amplifiers sitting on just nice conventional amplifiers at the top until we finally make it back to our equipment rack. Okay, this is a VNA, one of our workhorse instruments among many around here. VNA stands for Vector Network Analyzer. Vector in the sense that if you've ever used a vector in math, you know it's something that has both an amplitude and a direction. In our case, we think of our microwave signals as vectors. They have an amplitude, and as it's going around in its cycle, repeating again, that's like 360 degrees in a circle. And we want to know exactly what the direction, the phase of the signal is. That's what makes it a vector analyzer. What makes it a network analyzer is it has more than one port. So this one has 4. We're just going to be using 2 in a little demonstration here. We're hooked up to ports labeled 3 and 4 right now. I can grab this guy. This is where we're going. This is one of our 3D cavities that we will mount on the fridge. And we're just doing a little room temperature test on it. We're hoping that it has a frequency of around, I think, 6.7 gigahertz. And we're just going to measure that before we cool down and make sure that's what we want. We know where to measure when it gets cold. This is something that does have a little qubit inside, but we won't be able to see anything quantum about this at room temperature. We're just looking at what the cavity does. So putting that aside, if my cables and connections are good, that trace didn't change when I moved it. And what this yellow trace is just magnitude. So this is really just kind of the length of the vector on the vertical scale, and the horizontal scale is frequency. You see this blue light here means we're sending signal out through port 3. We're measuring what comes back on port 4. So if I have this on a marker, I just manually put that on there. I'm reading out about 6.65 gigahertz, not bad. That's about where I wanted it. I can turn on another trace here, and it's very, very sharp transition in angle. So typically what we'll do if we're reading these out is we'll be taking a trace very much like this, but instead of scanning through many frequencies, which takes a long time, we want to read out very fast. So what we'll typically do is send in a single tone, maybe just a little off center of what the center frequency of the cavity is. To see the state of the qubit, like a 0 or 1, the state of the qubit shifts the frequency of the cavity just a little bit. Say this is when the qubit's in the 0 state. When it's in the 1 state, it might shift over to be where the 1 is. So in that way, we can send in a relatively large microwave signal into the cavity, look at the phase of its return, and depending on how the phase is shifted, we know the state of the qubit without talking to it directly. That's called dispersive readout. You're kind of talking to the cavity around the qubit, and the qubit has a very subtle effect on the cavity that we can read out with high fidelity. And that's how we usually talk to our qubits. In this case, we're not going to see any dispersive readout because our qubit is at room temperature. It's not even superconducting, much less in a coherent quantum state.
One thing that the national laboratories do especially well is our ability to tackle big problems that have a long time scale. Developing the next generation of computing hardware is one of these problems, and that sort of commitment and a devotion to solving the big problems that are needed to bring the technology to the next level is the reason that the national laboratories like Lawrence Livermore National Laboratory are an ideal space for us to be doing this work.
There are constantly new technologies that are coming around and that we're exploring. Having expertise in lasers allows us to quickly turn over and look at any applications that might come out with lasers. Having expertise in superconducting materials allows us to go and explore superconducting systems very quickly.
If we never iterated, we wouldn't have this fridge open behind us, right? We would just run. We got to open up and say, okay, we got a little data that gives me an idea. I've got this other device from the fab room that I want to put in now. Let's warm up and swap it out with another one. I've got 5 new things I want to try. You don't know what you're going to learn until you try it. That gives you some new ideas to try something else out. So you got to have amazing tools, people who are good at using the tools, very creative scientists who can imagine new things that we don't know to be true yet, check that they're true, and then when you discover something new, well, you've done some science.
Quantum technology isn't science fiction, an abstract concept, or a microscopic world separated from our reality. The truth is, we've always lived in the quantum realm, and we're just awakening to what that might mean. For more information on the laboratory's quantum experiments, visit Science and Technology Review.